So again, welcome everybody who already joined. I think we can wait 2 more minutes, but I just wanted to start the recording with this slide. I'm really excited about today's seminar. It was a long way coming, so I'm really looking forward to discussing with you today, but we're also having this seminar today in 2 contexts. So this is our bi-monthly institute seminar, as well as the LibreHub seminar, which is a new seminar series we're starting from our John Zuckerberg Fund initiative on open hardware for bioimaging across Latin America. So this means there are going to be a lot of people from our institute joining, but also people from across Latin America who are interested, and open hardware advocates from around the world. Okay, so now that the video has already started with this slide, I'll stop sharing and we can start trying to share your slides, Richard, to make sure that that's all working before we actually start the presentation. Yeah, I already stopped sharing if you want to try.
Okay.
Yeah, that looks great already.
Excellent. Right, that was remarkably smooth.
That's the way we look. Okay, so we can wait just 1 more minute or so, and then we can jump right in, and of course, then have a bit of discussion time with everybody at the end. And again, just so that everybody is aware, in this LibreHub seminar series, we are recording all the seminars and we upload them on YouTube afterwards with subtitles in Spanish and Portuguese. Actually, they're automatically generated, so you can do pretty much any language. But this means that people who can't join the meeting today can still look at all the exciting open hardware bits later and hopefully start using them.
And just to confirm, I should aim to talk for something like 30 minutes?
Yes, around that would be good, so that we have a little bit of discussion time also.
Perfect.
It's not a strict timing.
Don't tell me that.
Okay, people are still dropping in and out, but I think we already have a decent crowd. So whenever you like, Richard, you can just go ahead and, well, I'm going to introduce you again. So I think a lot of you in the call have already heard of him and also of the OpenFlexure Microscope. We have various of those in different project contexts, as well as courses that we organize here in the Institute. I have probably at least 5 OpenFlexure microscopes in my office. And so it's particularly exciting to hear from you. But we already know each other for some time, so it was particularly exciting for me to see the early prototypes of the OpenFlexures back in the day in Cambridge, and to have seen to what nice project it has grown. And of course, the OpenFlexure is not all you do, but there's a lot of exciting photonics research that you're doing and other related open hardware projects to solve this accessibility of equipment. So it will be very interesting to discuss on all of these aspects with you. Thank you very much for being here with us.
Great, thank you. I heard something very strange there, but I'm going to assume everyone can still hear me.
Yes.
So, this is not a toy, despite the automatically generated PowerPoint alt text. It's made of colorful plastic, it fits in a shoebox, and it costs less than an Xbox. Nonetheless, it's a serious piece of scientific equipment, and I'm honored to have a little time to talk more about it, and about the community that has grown around it. I usually give a title along the lines of Microscopy for Everyone, and that begs the question, why does everyone need microscopy? Well, there are lots of reasons: education, scientific research, environmental monitoring. But the one that has really driven the OpenFlexure project is this. This is a Plasmodium falciparum. It's the parasite responsible for malaria. And every year that affects about 200 million people, and it kills about 500,000 people. And a huge proportion of those are children under the age of 5 in sub-Saharan Africa. As we've gotten better as a species at fighting malaria, these numbers are actually much less bad than they were 10, 20 years ago. But that makes it, if anything, more important that we have good diagnostics, because it's now a very bad assumption simply to treat everyone for malaria and send them home with antimalarials, whether or not the test says that's what they have. Doing that now risks failing to treat life-threatening fevers with the right drugs. It leads to drug resistance for malaria. And so good diagnostics really matters. Microscopy, specifically bright field microscopy of a gene-sustained thin and thick blood smear, is still regarded as the gold standard for malaria diagnostics. It's more accurate and more quantitative than the rapid tests. The OpenFlexure project makes automated digital microscopes available at what I'm going to call a manageable price. So these are not orders of magnitude cheaper than the microscopes that are being used at the moment for malaria diagnostics, but they are an order of magnitude smarter than those microscopes currently are. And digital microscopy has a lot of advantages. It enables proper record keeping. It means you can do really meaningful quality control at every sample level, rather than just testing the technicians once a year. And thinking of the technicians, often they're the really tricky part. And a digital microscope can really help with the training of technicians, because you get around that issue where you never really know what somebody else sees when they look down the eyepieces. And instead of comparing a picture of your eyelashes down an eyepiece to a picture in a book, all of a sudden you can compare one image on a screen to another image on a screen. And so it really helps to enable technicians to improve their training, and indeed to seek a second opinion from someone who might be located quite a long way away, without having to physically transport technicians or samples. And lastly, the whole thing is designed to be locally producible, as I guess at least some of you are well aware. And in the context of sub-Saharan African malaria diagnostics, and indeed in many other contexts, being able to produce something locally is far more valuable than just making it cheaper. It cuts out a huge amount of import faff, to use the technical term. It means when something breaks, you're much more able to repair it locally. And of course, it keeps a lot more of that high value service and manufacturing local. And so it builds sustainable local high-tech industry, which I think is really appropriate for the kind of funding that we've had for this project. So I'm talking about microscopes. What do I mean by a microscope? Well, here's a picture of what many people would mean by a research microscope. It's an optical microscope, and you'd be forgiven for thinking that means it's mostly about the optics. But actually, 99% of the size and weight of an optical microscope is mechanics. Yes, there's quite a lot of the microscope devoted to lenses and objectives and so on, and it accounts for probably more than 1% of the cost. But a vast proportion of the engineering effort goes into making sure everything's held in the right place, making sure you can move the sample around precisely, making sure it doesn't drift out of focus. And so if you want to produce a microscope, actually you spend a lot of time producing the mechanics. And so importing the optics and producing the mechanics yourself is a really good compromise. And the OpenFlexure project, I guess, asks the question, can we do this mechanical positioning in a package that is smaller and lighter and much easier to produce? Well, I wouldn't be giving this talk if the answer was no. What's the advantage of 3D printing it? Well, all of a sudden it's small. So it's about 20 by 15 by 15 centimeters. That means you can fit lots of them into a small space if you want to parallelize. You can put it in an incubator or a safety cabinet. You can stick it in a shoebox and carry it to a remote location. It's relatively inexpensive. So the parts cost, and I stress the parts cost, please don't think that I'm equating this to what you would pay for a microscope, because there's no profit margin or sales or support allowance in there. But about £200 of parts will make the top of the line high quality optics version with a motorized stage. And again, that opens a lot of doors. And I would say this is not the same thing as a £20,000 motorized research microscope, but it can do a lot of the same experiments. It's also really easy to replicate. And because we've used 3D printing for all of the complicated mechanical assemblies, and because it mostly prints in one piece, the barrier between the digital designs and the physical reality is much lower. That opens a lot of doors for collaboration and for sharing. And I think really the strength of the project is that we can share it really very freely, and we can then get other people's improvements and pull them back into our design. And I think the aspect of OpenFlexure that I like the most is that it's a global community project. I'm kicking myself here. This slide is woefully out of date. We're now up to, I think, 41 countries where we've colored in green on this map. I noticed Chile's not even on there, which is particularly remiss of me. So it's been used in a lot of different places. Key to this is the fact that it's released as open hardware. So the first release was 2016, and all of the project development has been in the open ever since. And I'm a big believer in making things open early and in trying to document them as you go along, because my experience is if you keep everything a secret and then just release it at the end, for starters, you miss things and your documentation is just never complete. Secondly, you get almost to the end and then stop because reasons stop you. And lastly, if you get to the end, then you have to have a difficult conversation with your university's IP people about whether or not you're actually allowed to release it openly. Whereas if it's been open from the beginning, there was never any single point in the project where you released a big chunk of IP. It just kind of grows organically, which is a bit sneaky, but very helpful. And I think it works particularly well as open hardware because it's so easy to replicate. And it's easy enough to replicate that you don't have to assign a postdoc in several months. You can give it to a master's student. The resources required are quite proportionate. And lastly, we've put quite a lot of effort into community building around the microscope, rather than just having our GitLab repository, which we found put a lot of people off because it's really designed for software developers. We have a friendly forum, which has been a really great place to watch the community emerge, which is very nice. So my outline, don't worry, my outline comes some way into the talk. I'm going to talk a bit about how we actually make the microscope work, a bit about how we then have the kind of logical components of smart microscopy experiments, and how that filters into creating smarter, more joined up labs, and then have a whistle-stop tour around the OpenFlexure community. So OpenFlexure, the clue is in the name that it uses flexures. What does that mean? Well, in a microscope, you need to be able to move things around very precisely and then keep them in the right place. And typically how this is done is with a mechanical dovetail. So you would machine two pieces of metal that fit over each other. One of them slides up and down on the other. And so it's got to move up and down in a straight line without wobbling, without jamming. That means you need very precise tolerances on all the parts so that they fit tightly, but not too tightly. You need to use hard materials, which are then, of course, quite difficult to machine because otherwise it wears down over time. The surfaces all have to be smooth so they slide nicely, and so on and so forth. It's a difficult mechanical engineering problem, and there's a reason this stuff is expensive. If you just try to print that, it's a bit rubbish. 3D printed plastic has rough surfaces, the surface tolerance isn't very good, and it's quite soft, so even if it works nicely when you first print it, it'll almost certainly get less good over time. This is why Thor Labs are not worried about releasing all of the STLs on their website, because ultimately, if you 3D print those, you don't have a good stage. In the OpenFlexure project, rather than simply copy a design that is intended for metal, we exploit the fact that the plastic is flexible and soft. And so to achieve the same motion, we use a flexure mechanism. The thin parts of this, I don't know if you can see my mouse, but hopefully you can spot the thin bits of plastic that are actually bending.
Your mouse.
They are hinges in the same way that your shampoo bottle has hinges. And actually, they're really very repeatable and precise. And this is how we do basically all of the motion control. And that parallelogram was the working principle behind the first version of the microscope. Well, okay, technically the second version, but you don't want to use the first version. And so you can see that parallelogram there. I then added another pair of parallelograms to do X and Y motion, and I had a functioning microscope. The mechanical design of that one was pretty wobbly, but I continued evolving it on my Friday afternoons. And after a sleepless Sunday night, I flipped the whole structure around and we arrived at something that is quite close to the microscope that I have today. And I took this video. This is the most boring video I've ever included in a talk. It's 2 6-micron beads and it's a time lapse over a week. And what I want you to take from this video is that they don't move very much. And that's a good thing in a microscope, right? You want to be able to leave your sample in place and have it not drift too far. It has gotten a little bit more complicated than the designs I showed on the previous slide. And we now have something with kind of all of the bits that you'd expect in a typical research microscope. We've got a little condenser module up at the top. It uses standard objective lenses. There's an XYZ translation stage, some more optics and a camera, and then a case that contains all the electronics. And I'm now going to attempt to show you one. I think I probably need to turn my virtual background off so you can all see my garage lab. So this is the very latest version 7. You can see it looks pretty much like the render. It's got some motors attached. We now have a nice little drawer that integrates the Raspberry Pi and the motor driver board. And you can see I have reluctantly started printing it in slightly more grown-up color schemes than OpenFlexure Pink, because we are spending a lot more time talking to people about medical certification. I might just spare you all sight of my garage from there. That was just in case it didn't work. This is a talk about a microscope, so it would be a bit unfair not to show you some pictures, although actually, really the novelty of the OpenFlexure microscope lies in the mechanics. There are lots of cool projects doing low-cost, accessible microscopy and imaging. I have to say, our optics are perfectly good. They have the advantage of being nice and simple and reliable. But this isn't primarily a project about optical innovation. What we offer the world is good mechanics. And it's really nice to see that actually a growing number of people are building on that foundation to put other interesting optics in. And hopefully one day I will be one of those people too. So we can image in bright field. This is one of our blood smear images taken with 100 times bright field. We can also set it up to image and reflection. And these, I think, are some graphene flakes. This was a student project trying to see if we could automate the detection of monolayer flakes in mechanically exfoliated graphene. We can do polarization imaging. And indeed, there's someone working on adding a rotating polarizer so we can do slightly more sophisticated imaging. I have no idea where that laser pointer came from. Apparently it's in my PowerPoint slide, but I can't delete it. And we can also do fluorescence. And yeah, you just put in a miniaturized epifluorescence cube. We don't do any kind of funny low-cost hacks. This is exactly the same format of fluorescence that you would get in a typical inverted research microscope, with all of the advantages and disadvantages that that entails. Namely, it's a bit more expensive than side illumination. On the other hand, you probably get more intense and more even images. We have put some work into trying to quantify how good the imaging is. We can take an image of an edge because we were keen to do this with a relatively cheap calibration target. We can do some differentiation and arrive at a point spread function. And to cut a long story short, we reckon we're basically limited by the quality of the objective that you buy, and it's pretty close to diffraction limited imaging. As I've said, one of the goals is to make it easy to bring your own optics and customize this with all manner of exciting different setups. And the delta stage is a slightly different geometry where the sample moves in X, Y, and Z rather than moving the sample laterally and moving the objective to focus. And the big advantage of doing it that way around is that the optics are then completely static. So you can couple lasers or projection systems or whatever you like into the objective without having to worry about hitting a moving target as you move the objective up and down. And indeed, a number of people have built on this to do super resolution imaging or phase imaging or structured illumination. And it's really cool to see the YouSeeToo team have got an adapter so you can put this on top of a YouSeeToo system, take advantage of all of our hard work making nice microscope mechanics, but also get the benefit of their easily swappable modular optics. This slide recaps that very boring video. And the point here is just to say you can quantify how much it drifts, and the answer is not that much. It doesn't do as well as a really nicely designed monolithic metal microscope. On the other hand, it does do considerably better than many commercial microscopes that I've used. And particularly when you add in the fact that it's all motorized and you can therefore servo control for drift, particularly over long times, as the phantom laser is helpfully pointing, then it becomes really useful for long experiments. We've put quite a lot of effort into the software. I hope this video comes across nicely over Zoom. It's probably a bit jerky, but this is real time. So it takes only a few seconds to do a proper image-based autofocus, largely thanks to some cunning trickery involving the JPEG camera compression. And of course, a really good autofocus is an important part of any microscope experiment that runs longer than about 5 minutes or moves the stage any meaningful distance. And indeed, we can move the stage by a meaningful distance. This latest result comes from PhD student Joe Napper's work, where he has not only gotten it to scan and stitch the image, it's now doing closed loop Z stacks. So it will move through the focal plane, taking images as it goes. And in real time, it's checking the sharpness of all of those images to make sure that your Z stack is centered on the focus. And that means that if this scan completes without any errors, I am very confident that all of the images are sharp. Because previously, it was a real problem that just occasionally the autofocus would go wrong or something, and there was no code in there checking. And so you would come back after leaving your microscope scanning all day, and your scan wouldn't be good. And that's really annoying. So now we're able to do real-time error detection and in some cases error correction to make sure that you get a sharp image every time. You've seen that once already. We can do a similar thing in X and Y, so we can calibrate the relationship between the image and the microscope stage, and that's built into the software, so you can do it individually for every microscope. This is just demonstrating that we can do a sort of click to move. And that, of course, then enables you to do image analysis and then to move the microscope based on the features in the image and so on. It's another kind of staple building block of smart microscopy. We can even model things like the mechanical backlash of the stage, but I probably shouldn't bore you with the mathematical details there. Too far. What I can say is that if you want to move the microscope around a predefined path, then this closed loop move enables you to pick a much more, enables you to make a much more accurate move. So the error without that closed loop correction is probably a few microns per move. After you've done the correction, you can get it down to a couple of 100 nanometers if you're very careful. All of this runs on Web of Things software. A central theme of my research, even before I was involved with the OpenFlexure Microscope, was trying to figure out how to automate lab equipment without going absolutely spare or spending my entire life programming. Or at least I'll spend my entire life programming, but I don't want you to have to spend your entire life programming as well. So the architecture we've settled on is that the microscope embeds a Raspberry Pi. That's one of the things you see at the bottom of the bucket. And that Raspberry Pi runs a little web server. So you can plug a screen into the microscope and use it as a standalone thing. But more usually, you would access it as a network server, either from the Raspberry Pi, so it acts as both client and server, or from your laptop or any other computer on the network. And the nice thing is that in the last kind of 3 to 5 years, we've seen a lot of standards emerge for Internet of Things devices. Now, these devices are mostly things like fridges or light bulbs or CD players. Very few of them are as complicated as something like a microscope that has to manage data sets and calibrations and so on. Nonetheless, it means that there are open standards and, crucially, quite well-written libraries behind them. And so we've taken advantage of that to make the OpenFlexure software. And it's really cool to see other open and hopefully some non-open projects also using this method of communication between different instruments and scripts and so on. So this highlights a paper together with the YouSeeToo team. I believe Benedict has already talked at one of these seminars. And also ImJoy, which is a very cool in-browser image analysis and deep learning project. And we also linked it up with an Opentrons pipetting robot. So we've really got a meaningful integration of several different lab components. Everything runs from a Jupyter notebook in a web browser. And this is lovely, but I think the point that this doesn't make very well is that we're not tied to using that Jupyter notebook. Actually, because you can control stuff through the Web of Things, you can use whatever language, whatever operating system you like. You don't have to use the same framework in your control script that I'm using in my instrument code. And that, I think, for me is transformative, because it means that all of a sudden, you really can reach the goal of having a basically self-documenting set of commands that you can run from the language of your choice, rather than having to go, oh, well, this one's really well supported by Micromanager, but that one's only going to work at ImSwitch. And now I end up re-implementing everything so that I can control an experiment all at once. So at this point, I'm going to change tack slightly and give what is usually the last slide of a presentation. I'd like to thank the large and growing team of people at Bath who have done most of the core developments and the work that I presented here. Our very close collaborators at Bongo Tech in Tanzania, who are responsible for co-developing the microscope and all of the Tanzanian production. So we have some results from our Tanzanian healthcare collaborators, and all of the microscopes they use are produced 2 hours down the road in Dar es Salaam. So I'm not shipping microscopes out there. They're using Tanzanian microscopes, and when they go wrong, they send them back to BTEC, and the team at BTEC will fix them. And so we really have this local infrastructure working, and the challenge is trying to convert that from something that's part of a research project to a viable commercial enterprise for BTEC. I should also mention the team at Cambridge, particularly Samuel, who is really strongly involved. Samuel's led most of the recent work on the Delta stage. And I'll give you our wonderful composite team photo. We've never all been in the same place at the same time. I am hoping to have a small OpenFlexure workshop in Bath this July. And that will get together a subset of the community. But I think it will be really lovely to have, for the first time, people from a bunch of different places who are all part of the project. But of course, that team photo only tells a small part of the story. I've mentioned already that we've been working for a few years with Joram at Ifakara Health Institute. So this is Joram in his lab with his microscopes imaging some blood smears. This is a print farm in Kenya where they were producing microscopes using filament made from locally recycled PET plastic bottles, which I just find incredibly exciting. We got the big stockpile of microscopes from BTEC's initial production run when we were just trying to figure out whether they could produce them reliably. Here's a little shot of Julian using an OpenFlexure microscope in the rainforest in Panama. In fact, we've even had a student from Cambridge, Hannah, using an OpenFlexure microscope on the Antarctic ice to look at snow algae. So I can verify that it functions at -20. And it's been enormously fun to support a whole pile of different collaborators doing exciting things with the microscope. One of these is the team at the University of Strathclyde. They'll be my next door neighbors later this year because I'm moving to Glasgow myself. And they added a laser and a fancier camera, and we're able to do super resolution imaging using nanodiamonds, which is, I think, pretty cool. We've also had a very enthusiastic collaborator appear. He's based in Houston, but has various collaborators all around the world. And he's using the microscope in his pathology research and teaching, often because he's able to go on a visit to introduce a new endoscopy technique, for example. But how do you get the samples back for analysis when there's no slide scanner at the institute? And the answer is he leaves them an OpenFlexure microscope, which is very cool. And we're working on supporting that project better with improved scanning and stitching and tiling in the stock OpenFlexure software. But if you want to look at some really beautiful biomedical images, he has a collection of teaching resources that are openly available for people to use, all acquired with the OpenFlexure microscope, which is lovely. I've mentioned many times malaria diagnostics as a motivator for this project. And so that was what the UK funding agency funded over the last 4 years, together with Ifakara Health Institute, who are our health scientists, and Bongo Tech, who are the engineers, and the company that we hope will eventually be medically certified to produce them. Clearly, we already have microscopes working in a clinical lab. They're good enough. But that's only the start of the journey of making a medical diagnostic. We have improved the casing to make it more rugged. We're improving all of the error correction and the commissioning procedures and the calibration stuff so that we can really be sure that when a microscope leaves their factory, it's in tip-top condition and it works as it should. And after that, the next step is to convince the Tanzanian Medical Devices Authority that this is ready to be sold as a medical device. That is a long-term project, but it's one that we really hope will happen, because it will be incredibly exciting for this to be the first digital in vitro diagnostic in Tanzania that is domestically produced. All of this community building and collaboration really sits on top of a huge amount of effort in documentation. I know that's a cause close to Toby's heart. We have found that good assembly instructions are just absolutely crucial. Julian, over the last couple of years, has rewritten them at least twice. We've replaced all of our photographs with renders, which are generated automatically every time we update the CAD designs. The theory is that this should mean they're perpetually up to date and they're always consistent. Because what we found was that if you change something even slightly, you then either have to retake all of the photos, or everybody gets very confused why the photos don't quite match the parts in front of them. But there's also lots of software documentation if you want to program the microscope. And this is very much enabled by all of the kind of Web of Things technologies that will handle things like nice automatically produced documentation that is consistent and up to date. We have an interactive configurator that lets you pick how you want to build the microscope and download the right set of STLs. And I should mention that the assembly instructions, Julian has put a lot of effort into writing Git building, which is a system for embedding metadata into Markdown instructions and formatting them nicely. And finally, I'll say that we try and summarize everything on the website and the forum. The forum, I think, it was absolutely key to launching this as a community project, because there are so many more people that get involved on the forum than people who feel comfortable contributing on a Git repository. And it was a real eye-opener to me, actually, when we set that up. All of a sudden, it went from about 5 people involved in the project to about 100. And so anybody who's interested, I would recommend you to pop onto openflexure.org and say hello in the forum and join that community. So with that, I will stop talking and leave some space for questions. And in lieu of a conclusion slide, I'll just put up a bunch of different pictures that have something to do with the project. Thanks very much.
Thank you so much, Richard. It's absolutely fascinating to hear about the ecosystem of sort of tools and solutions you've been able to develop around this project, the people who managed to get involved, but also this work of actually applying them or supporting communities to apply them locally. I think it's really inspiring, and this is clearly why I always use your project as an example, just most recently at the Bioimaging Summit of the Chan Zuckerberg Foundation, because this is just the benchmark, I think, for anyone in this area for their projects to go in this direction with, and we're certainly trying to learn from you and use these systems. But yeah, so thank you very much for sharing this with us. But I don't want to ramble out too much as well, because I'm sure that there are a lot of questions also from the whole audience. So please feel free to interact with the speaker. Okay, while we're waiting for people to summon their courage, I'm sure that there are interesting comments in some people's minds. I'm going to ask you something that we have exchanged in the past, but now I have the opportunity to ask you in person again. So for some applications, it's nice to look at samples that are a little bit bigger. So for example, we've tried to use the microscope for some pollen microscopy, but the standard procedures of that microscopy require that you scan a whole glass slide, which is a little bit bigger than the movement range, for example, of the stage. Or we use it for microfluidic chips that usually are a little bit bigger. And so we're very interested in something that has a little bit more movement range. Is there something that you've thought about? We've tried to do it ourselves. I realize that the Flexure mechanism is sort of a little bit limited there, but it'd be interesting to hear from you.
Yeah, I think the range of travel is definitely the hardest thing to improve in a Flexure stage. You can improve it a bit, but getting over a whole glass slide is going to be quite hard, just because you end up basically making the levers longer in the Flexure mechanism, and at some point the whole thing just isn't very mechanically stiff anymore. What I have done is I've made a version of the microscope where I got rid entirely of the X and Y axes. So you just have the nice Flexure focusing mechanism, and then a flat laser cut stage on top. So for imaging bigger stuff, what would be really nice is if someone could adapt like a 3D printer XY stage or something to sit on top of that. And then you'd be able to take advantage of the really nice high precision focusing stage, but usually you can get away with less precision in X and Y. I think that's what I'd like to do. I have no idea when I'm going to find the time to do it. And if somebody wants a project for a good mechanical engineering student, I think they could have a lot of fun with that. So the flat top microscope is documented on GitLab, but not particularly shouted about in scientific literature because nobody's really picked it up and run with it yet. But I think it would be very cool if that happened.
That makes a lot of sense. We are certainly going to try this with Pierre, so we've already discussed it. And then for the top stage, we wanted to try the new design that's shared with the YouSeeToo framework, sort of to automate this metal stage that has a big glass table in the center. So that's especially nice for microphysics, where it's usually quite messy and you're squirting around some liquids, and it's kind of nice and clean. That sounds really good. Yeah, there are a couple of examples how we use the microscope also here locally in our institute. So we just made a whole class set. It's not 100% ready actually, but almost, of OpenFlexure Microscope to use in a prototyping course. Our colleague Cesar Ramirez has made one for his research, and Fernando also has a couple of projects where he uses it. He's also in the talk. I don't know if he wants to mention those a little bit to tell us about it. If not, anyone else is very free to unmute, please, and bring forward your questions. Don't be shy. So we usually have quite nice discussions in our seminars, so I'm not sure why people are so shy today. It's such a, there's so many facets of this project, so I'm sure that there are many things to ask about. Well, fair enough. So then it's me ask you a couple more questions. So I also, well, I share your vision in pretty much any way, every way. So, so I think that's one of the reasons why I'm so excited about it. But also one of the things that I find very promising is to run lab equipment on some kind of web server and be able to connect a lab infrastructure and increase the automation of workflows. Is there something you're particularly excited about in the future, something that's coming up, things that you're keen on linking together, for example?
Well, so I think what really opened my eyes to that was postdoc Joel Collins, who sadly has now found employment elsewhere. But he was the one that really got into the Web of Things architectures. And probably the biggest development was the W3C. So this is the standards organization responsible for a lot of the web, have released the Web Things standard, which is, I can't remember exactly what stage it's at. It's technically still mostly in draft form, but it's now pretty stable. And that kind of codifies how you map the actions and the properties of a physical device onto HTTP endpoints, so the kind of the web servery bits. And so in the last few years, there have been a lot of very well supported tools for things like automatically documenting your web API or making a client library for that web server in any language. And we've just started to get the OpenFlexure software to the stage where we can now use those tools. So that's what produces the nice API documentation, for example. What I'd love to do is push lab things a bit further and make some libraries that enable other people to do the same thing with their instrument with a lot less effort. So lab things is already a project that you can get. The server side of it only exists in Python at the moment, but there are a couple of folk working on doing it on ESP32, so an embedded microcontroller platform. And that then really opens up the door to having a lot of little low-cost gizmos that you can integrate into your experiment. Even if it's just having a relay to switch something on and off, having a little ESP32 board that takes care of that makes life a lot simpler. And in these days where actually even getting hold of one serial port on a computer is a pain, by the time you need 10 or 20 little different devices in different places, managing all of those different serial or USB connections is a total pain. And so actually doing it with a little local network is a good choice.
And it sounds like it can help with cable management as well, which is always a problem for bioexperiments, right? You want to keep things clean, but then you have cables everywhere. Certainly,
yeah.
Microfluidics.
Yeah, I mean, it's an interesting question whether wireless or wired networks are better for this. I think even with a wired network, you can probably cut down on cable clutter a bit. Wireless is probably cleaner in terms of how many cables you need, but it's definitely worse in terms of reliability.
Okay, I have an endless amount of questions that I could still give you, so it's nice that I get all this time to ask you. So one thing that I find really impressive, this whole infrastructure that you managed to create with your team and your collaborators. So you have this documentation tool, this automatic rendering, the forum, the web server. So now, of course, that for someone who just starts an open source project, for example, it might look a little bit daunting. It's like, okay, which part of these are easy for people to take on board, for example, and copy? I mean, now, for example, hosting a website on GitHub is pretty easy. Which things would you recommend people to start off with? I mean, you mentioned that the forum made a big difference for community engagement, for example. Is it very easy to launch?
So the forum, we have our very own discourse instance, which they gave us because we convinced them that we were a big enough open source project that we qualified for their open program. If you're just starting something, that's not an option. On the other hand, I believe it's relatively easy to get a sub forum on the Gosh forum platform, which I think is actually also provided by the same discourse service. And so Gosh is a big community that supports lots of open hardware activities, as I'm sure many of you know. I would say setting up a forum like that is probably the best thing to do. And if you can get a Gosh sub forum, it's probably quite a low effort thing to do. Having decent version management, so having somewhere that you put the files where you can say, yes, this is the up-to-date version, and where somebody else can go, okay, I've changed this, would you like to include that? I think is really important, because otherwise you just spend all of the time that you have to work on the project emailing people different versions of SDL files, which I can attest is incredibly annoying. Thanks for that link. Yeah, I think the stuff we've done around automatic renders and so on, that's a lot more work. And something happened there. So the Git building instructions, you write in Markdown, and there's then a processor that will turn that Markdown into a website, and do all of the things like counting all the different screws you've used to produce a bill of materials that's accurate. That's quite easy to integrate with platforms like GitHub or GitLab. And so the intention, at least, is that once you are happy uploading some designs to GitHub, it shouldn't be a lot more effort to then get it to automatically compile your instructions into a friendly website. I think with the OpenFlexure project, we've achieved a big enough user base that it's worth putting quite a lot of effort into all of this stuff. And I see it very much as a kind of a test bed for what you can do. I'm realistic that I don't think it's appropriate for everyone to expend this amount of energy because it's not always justified. But I think it's really fun for us to explore what's possible in terms of, you know, automating all of the renders that go into the assembly instructions and all that kind of stuff, just so that other people can pick out the bits that are useful to them. And hopefully that ramble has passed through the bits that I think are most immediately useful. One of the things we'd love to do is come up with some software that makes it easier for hardware developers to use Git to manage the hardware files, because this could deliver an enormous benefit. But I think understandably, a lot of people are freaked out by the somewhat quirky command line interface that I think everyone I know that uses Git has at least one story of just losing a whole pile of stuff because they typed the wrong set of commands. And I think having better interfaces to that would really open a lot of doors, because I think once you've gotten over that hurdle, actually all of this automation and version management infrastructure is incredibly useful for hardware.
I admit to normally using the GitHub desktop app, which is really convenient, but it doesn't work, for example, for the OpenFlexure because the files are too big. There's some restrictions there. Well, in our project, we also have a little bit of web developer budget to do just, well, do a part of that, I guess, help with a little bit of an interface to write the documentations more in a sort of what you see is what you get style, but using this system, using the building system. But actually, I think at the moment we're still trying to find someone, and ideally like a local student or so who's motivated to take that on.
Cool. Yeah, I think improving the friendliness of that interface is key. Julian has made a lot of progress on an interactive browser-based editor for it. I think the challenge is that the architecture of it at the moment relies quite heavily on server-side processing, which then means it doesn't scale terribly well, because either you need someone to install and run their own Python-based web server, and as anyone who's tried Python dependency management on multiple platforms will tell you, that's just annoying. Or you end up trying to set it up running on a server, at which point there are a lot of security issues and just resource issues, because the interactive editor involves reprocessing all the markdown source every time you press a key on the keyboard, which doesn't scale to lots of users. I see there is a question in the chat, which is, what's the average cost of the latest version? So to break it down, the latest version in its kind of fully featured configuration, you end up spending ballpark sort of £30 on the camera, between £30 and £50 on the Raspberry Pi, and there's probably £20 or £30 of accessories that goes with that. So about £100 on just the basic computing bits. Then probably another £100 on the optics if you use a generic microscope objective and a tube lens. And maybe £50 on the motorboard and the motors. You can do it more cheaply than that, but if you get a board made, that's about what it costs. And then the kind of the nuts and bolts and other bits, maybe the parts costs about £10, and the plastic is about £5. So it's somewhere between £200 and £300 of parts. I think if you want to
just for the general audience, so a pound is just a little bit more as $1 basically. So yeah, so it's similar. Yeah.
Yeah, I often joke that if you convert prices from dollars to pounds, you should just use a 1-to-1 ratio. Unfortunately, if you convert prices from pounds to dollars, it's not the same. So you have to increase it slightly. Yeah, but of course, if you're happy using just the lens off the webcam instead of the microscope objective, then that saves you nearly half the cost. And if you don't need the motors, that also saves you a chunk. There's another question. There's no kind of inherent reason that it has to be a Raspberry Pi. I have to say bits of the software are quite specific to the Raspberry Pi, and particularly the way the camera drivers are written on the Raspberry Pi. So it would take a little bit of effort to make it work nicely on another platform. In principle, it could work nicely on a Jetson Nano. In fact, Benedict Diederich of the YouSeeToo project, he has run it on a Jetson Nano. It works. It doesn't do the nice autofocus anymore. That's the major thing you lose. I'm currently doing a big rewrite of the software, or at least reorganization of the software, that should make it more possible to support other architectures. We really like the Raspberry Pi because it just makes everything accessible. There's a huge support community behind the Raspberry Pi, and there's a big ethos of helping people learn how to automate stuff, which makes it a very appropriate platform. Something like the Jetson Nano is probably a lot more powerful, and if you want to do embedded machine learning or whatever, it's exactly right. It's just that there's not that big friendly community behind it, which I think has really helped the project take off. On the other hand, now you can't buy either a Jetson Nano or a Raspberry Pi for love nor money because of supply shortages. So pretty much you scramble together whatever integrated computer you can get your hands on and make the best of it. I really hope that situation eases.
These are very good questions. I would like to, the hour is pretty much up, but if I may, I would still ask you one last question and pick your brain sort of on our mission to disseminate this kind of approach of equipment building across research labs in Latin America. So obviously a lot of these examples and developments still don't come from places like Tanzania, even though of course now you've definitely helped, I think, and supported the creation of a local hub where things do come from now, and some board designs come from there. But in most places, these things are still not very much used and not very much known. So usually when I talk about these things, it makes a lot of sense to people. It makes sense to people in rich places to say, oh, well, it makes people in less resourced places should obviously follow this kind of path. And to people in low resource settings, it also makes sense usually, but it doesn't necessarily mean that people are doing it or are sincerely planning on getting into it. So what do you think can we do to move in that direction? It's a difficult question.
Yeah, I mean, I think we have put a lot of thought into trying to lower the barriers to getting involved in development as well as just use. I think I try quite deliberately not to make too big a distinction between things that are useful in resource poor settings and things that are useful in very rich research labs, because ultimately I think my aim with this project is to produce a research tool that's useful to everyone. I want this to be useful to someone in a research lab in the UK, because if it's only something you use because you can't afford the proper one, then the people using it are always going to be second-class citizens. And the intention here is to make a tool that is good enough that it's not your second choice, well, we can't get the proper one. It's actually, you know, I want to do an experiment where I have 5 microscopes in a fume hood. OpenFlexure microscopes can do this. Almost nothing else can. Because I could spend £100,000 on Zeiss microscopes, but then I'd have to incinerate them after they're contaminated, and that would just make everybody cry. So I think there's a delicate balance there. But encouraging people to get more involved with the development rather than just the use. I think I have had to refine my expectations on that a bit. I think one of the important things to do is to create opportunities for getting involved with the development without having to learn all of the complicated software toolchain. So for example, you can pick whatever CAD package you like, but if somebody else wants to contribute, they probably want to use their CAD package, and it's probably not the same as your CAD package, and that's a big barrier. And so what I found was that actually opening it up on the forum and letting people just go, hey, I made this extra thing, I use a different CAD package from you, so I probably can't integrate it back into the main repository in the way that you do with software, but here are some useful files, and here are some pictures of what I did. And I think it's key to value those contributions and to celebrate them. And in fact, most of the contributions to the project have been like that. There are relatively few places where someone has sent me a merge request on GitLab and I've integrated their OpenSCAD code into our code base, because I have to be realistic and accept that most of the hardware development world doesn't work like that. And so I think the core of the project probably always will work like that, just because that enables all of the automated documents, and that set of consistent instructions is really important. But yeah, creating niches for people to do stuff and contribute meaningfully and customize it without having to learn all of the skill set of the core developers is a very important part of making it more accessible and growing it. And we do have a bunch of things that have come from, for example, BTEC. Like the motor controller board was basically entirely designed in Tanzania. And some of the adapters for using different cameras and other hardware with the microscope, that's also come from BTEC. And there are some kind of semi-deliberate gaps in the design, like there's no official case, because the box that you mount it in is almost always something that it's easier to figure out locally. And so if someone's going to manufacture this, I would much rather they put it in their own box and kind of put their stamp on that part of the design. And so it's kind of, yeah, it's semi-deliberately left not quite finished, to encourage, nay, force people to get a little bit involved.
Thank you very much. That sounds really great and makes a lot of sense. So I don't want to overrun too much overall. So thank you very much again for everybody to tune in. And I'm sure that a couple more people will also look at this later on YouTube. So I just thank you one more time for a very inspiring talk. Thanks, Richard.
Thanks very much.
Okay, so I'll just end the session here, but I hope that we also get to meet each other again soon. It was a privilege to actually see you just before the beginning of the pandemic, but it also feels like ages ago now. So I hope we'll meet again soon. Thanks.
Yeah, absolutely.